A student obtained the following data for the decomposition of nitrosyl bromide at 10 degrees Celsius. So we've got an equation here, not in the typical form we normally see it. We've got that half bromine. So if we multiplied by 2, we could get whole number integers for the coefficients, put it in a form we're most used to seeing. Not necessary, absolutely necessary, but at least it gets us into a form we've seen before, and there it is. Just multiplying by 2 to get rid of that half exponent. Okay, that may give us a clue going forward as well, but let's take a look at the data. So looking at our two rows, we've got the concentration in molarity of our reactant and then the time at which these concentration values were measured. So it wants to know in A, what's the half-life for the reaction starting at time equals 0. So by definition, the half-life is going to be the time it takes for this concentration, 0.365, to be cut in half. And so if we look at that and say, okay, 0.365, we can get an estimate based on the table for how long that's going to take. If we look at 0.365 divided by 2, it's going to punch that in the calculator. 0.365 divided by 2, we get 0.183 to significant figures, and there we go. And so that's the half concentration in the second column. And that's 4.74 seconds, so we have an exact answer given to us by the data that's observed. Okay, and that's by design for the question. Always got to have enough information to solve it here. So understanding what half-life means gets us to that point. And then in part B it says, well, what's the half-life if the reaction starts at 4.74 seconds? Okay, and so from there, 0.183 is our molarity. Half of that, there it is, 0.0915, and so 915 times 10 to the minus 2 is half of 0.183 molar. And so that's the second data point we have there, the time. But the time's not 14.2 seconds. Remember, the reaction started per part B. What is the half-life if we're starting at 4.74? So we've got to subtract that off from 14.2. When I do that, I'm just going to go use the calculator. I want to always be careful. 4.74. If you do it in your head, double check with the calculator. We get 9.46. But looky there, we've got an unknown digit there in that hundreds place, and so technically we should round off to 9.5 doing subtraction in this problem. So 9.5 seconds if we started at 4.74, and that's the new half-life. So half-life is changing. Now how is it changing? Well, that's going to be important for part C. What then is the reaction order if our reaction half-life is changing depending on the molarity that we are starting with? And so let's take a look at the three options that we have. If we look at a zero order reaction, we have a direct relationship between the half-life and the concentration that we start with, ace of naught here. And so if we multiply by 2 on the left-hand side, we're going to double the concentration on the right-hand side. 2K is a constant, so it's not going to change. So doubling the half-life, increasing it, is going to increase the concentration, or vice versa. Doubling the concentration is going to increase the half-life. Well, halving the concentration should cut the half-life in half. That's not what we're seeing in our problem, so we can rule that out. In a first-order reaction, it's just natural log of 2 over the rate constant, and so it's unrelated to starting concentration. So it's a constant no matter what half-life is for a first order. Well, our half-life is changing, so we can rule that out. Second order reaction, if we were to double the half-life, we would then cut the concentration in half. They're inversely related. That's exactly what we're seeing here. As concentration is being halved, cut in half, we are doubling the time it takes, and so we can say that there's an inverse relationship between the concentration initial and the half-life. And so that's a second order reaction. So we just come in here and say 2 or second order reaction for our reaction order. And so based on that, we want to calculate the rate constant. So we just saw that formula a second ago. The half-life was equal to 1 over the rate constant times that initial concentration. So if we're solving for the rate constant, we could multiply both sides by K and then divide both sides by the half-life, T half there, times A naught. So two terms we got to plug in, and we set those equal to the rate constant. Let's pick our time. Our half-life at the first interval here was 4.74 seconds. The initial concentration, if our half-life was 4.74, was 0.365. The final was 0.183. We want the initial concentration, 0.365. Keep our units here, molar. And we're going to divide that out. So I'm just going to say here 1 divided by 4.74 divided by, again, 0.365 gives us 0.578, or 78, excuse me, 0.578 inverse molarity and inverse seconds. So that should be even capital M there. Molarity to the -1, second to the -1, to 3 significant figures.